Welcome to Lesson 8, the refraction of light. Our goal for today will be to describe the law of refraction. This will be used to predict the direction of the refracted ray of light based on the medium in which light enters. And finally, we'll learn how to calculate something called the index of refraction. Let's get started. Refraction is defined to be the bending of light as it enters a new medium. This is caused by a change in the speed of light as it moves from one medium to another. And whenever we say the word medium, we pretty much mean material. So for example, a medium could be air, it could be water, it could be glass. It's the material that light is traveling through. Okay, and we'll sketch this in the picture below to make sense of what's happening. Okay, so first of all, let's do a little bit of labeling. This dotted vertical line, this is our normal. Then you'll see that we have a horizontal line. This horizontal line represents the interface between two different media. So think of it like a boundary. So for example, imagine that medium 1 is water and medium 2 is air. What happens as light goes from water to air? Let's take a look. So we'll sketch an incident ray of light, like so. Okay, let's label this incident ray. We'll label our angle of incidence. I'll use an I for that. And remember, we always measure the angle with respect to the normal. In this particular case, as light goes from water to air, it's going to bend away from the normal. You'll see this below. Okay, and the ray that comes out on the other side, this is the refracted ray. And we'll indicate the angle with an R. Once again, we always measure the angle with respect to the normal. So this is refraction in a nutshell. And let's just contrast it with reflection for a moment. Reflection occurred when light hit an object and changed direction. Notice when light reflected off of a surface, it didn't actually pass through the surface, but in the case of refraction, this is when light passes through a surface, and as it does so, it bends or changes direction. So on our picture, we labeled all of the following: the normal line, the incident ray, the refracted ray, as well as the angle of incidence and the angle of reflection. Let's discuss some laws of refraction now. The first law of refraction is as follows. The incident ray, the refracted ray, and the normal all lie in the same plane. We used this terminology in a previous lesson. It just means that they would all, for example, lie on a sheet of paper. That's what we mean. And secondly, the incident ray and the refracted ray are on the opposite sides of the line that separates the two media. Just to contrast this with reflection, the incident and the reflected ray were on the same side. Sometimes in the case of virtual images, we would extend the ray of light on the other side of the mirror where it appeared like it originated from. But in reality, both the incident ray and the reflected ray were always on the same side. Okay, carrying on, we have our second law of refraction. This one tells us that light bends towards the normal when the speed of light in the second medium is slower than it is in the first medium. So in other words, when light slows down, it bends towards that dotted line, which we call the normal. Let's show this in the picture below. So once again, the dotted line represents the normal. The horizontal line represents the interface between mediums 1 and 2. It's the boundary that separates the two. Okay, and imagine we have some incident ray of light like so. Here's our angle of incidence. If light travels more slowly in medium 2, then that incident ray of light will bend towards the normal, like so. Okay, this was a little exaggerated, but I just want to make the point clear, and that's our angle of refraction. On the other hand, light bends away from the normal when the speed of light in the second medium is faster. We saw this on the previous page, but we'll make a note here just for clarity. So once again, we have our normal. Let's say we have an incident ray of light coming in at some arbitrary angle. Here's our angle of incidence. If light travels faster in medium 2, it'll bend away from that normal, like so. Okay, so just to summarize, in the first scenario, the angle of incidence was greater than the angle of refraction, whereas in the second case, the angle of incidence is less than the angle of refraction. Let's put this to practice in the diagram shown. So please remember the dotted line always represents the normal. It's at a bit of an angle here, but don't worry about that. So let's just label it. This is our normal. We have an incident ray of light that originates in medium 2. Let's label our angle of incidence. Remember, this is the angle between the ray of light and the normal. And here we're told that medium 2 is less dense, and that ray of light is traveling into medium 1, which we're told is more dense. So generally speaking, everyone, light will slow down when it enters a denser medium. So in this case, we'll see the light bend towards the normal. Okay, please label your angle of refraction like that. And that's going to take care of that one. Let's do the next one. Here's our normal once again. Remember, it's always the dotted line. I'll label the angle of incidence. And it looks like it was missing over here, but let's assume it goes from a less dense to a more dense material, so it's going to travel slower in the more dense material. In that case, you'll see the incident ray of light bend towards the normal, like so. And there's your angle of refraction. Two more to go. I'll always label the normal just to make it clear. Actually, let's do that in both diagrams. Okay, so here's our incident ray of light with the angle of incidence. It looks like we're going now from a slower material to a faster one. In other words, a more dense to a less dense material. Light will always travel faster in a less dense material. So in this case, the light will bend away from the normal, something like this. And that's your angle of refraction. And lastly, we have an incident ray of light that is traveling into a slower material. In other words, once again, a denser material. So here's our incident angle. And because we're going from a faster to a slower material, light will bend towards the normal. Okay, so let's summarize. So what do we know about light so far? Light, remember, is a type of electromagnetic radiation. And it's a wave. It has wave-like properties. So light is really a type of electromagnetic wave, or EM for short. Did you know that nothing in the universe travels faster than the speed of light? This is actually what Einstein was famous for. So the speed of light in a vacuum, in other words, in outer space, but by the way, we can approximate air as being very close to a vacuum, not perfect, but the speed of light in air compared to a vacuum is about the same. So it turns out that the speed of light in a vacuum, as well as air, is on the order of approximately 3.0 times 10 to the 8 meters per second. I wrote that in scientific notation, and that's pretty much the number 3 followed by 8 zeros, like this. And if you don't remember how to go from scientific notation to standard notation, you just move the decimal 8 places to the right. So let me demonstrate. The decimal was normally right here between the 3 and the 0, and you move it 8 places to the right. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so light travels at 300 million meters every second. Just imagine that. It's the fastest thing in the universe. This is why when you turn on a light switch, the light instantly fills up the room. It really had to travel some distance, but it's so fast we don't even notice it. Now, the speed of light in a vacuum or air is this value. But anytime light enters a different medium, such as water or glass, the speed of light changes. Okay, so therefore, the speed of light depends on the medium in which it's traveling. So you may be wondering why the speed of light changes in different materials. The reason has something to do with the optical density. In this case, the optical density refers to the density of a material that is able to slow down the light. And something to help us quantify this is a measure called the index of refraction. For any medium, for example, air, water, or a vacuum, the index of refraction is defined to be the ratio of the speed of light in a vacuum compared to the speed of light in that medium. Another way to think of this is we're comparing how fast light travels in a medium, such as water or air, compared to its speed in a vacuum or air, because they're pretty much the same. And here's the formula that allows us to do this. We use the variable n to represent the index of refraction. So let's label. So n is the index of refraction. And it's equivalent to c, which represents the speed of light in a vacuum. Or air. Okay, and we looked at this earlier. It was 300 million meters per second, or 3.0 times 10 to the 8 meters per second, divided by v, which represents the speed of light in a medium. Okay, let's do some practice now to show you how we do these types of calculations. In example 1, we're going to calculate the index of refraction of sodium chloride, given that the speed of light in sodium chloride is 1.6 times 10 to the 8 meters per second. Alright, so let's use the GRASP acronym to help us solve this. Remember, it stands for given, required, analysis, solution, and lastly, paraphrase. So what are we given? We're given V, the speed of light in sodium chloride. In this case, it's 1.96 times 10 to the 8 meters per second. And I know it seems like that's all you're given in the question, which is technically true, but something that you always know is C, the speed of light in a vacuum. Okay, so what's required? Well, we were asked to determine the index of refraction, so we need to find n. In the analysis, we'll use the index of refraction equation, which is n equals c over v. And now we do a solution. So n equals c over v. Please go ahead and substitute. So for c, we plug in 3.0 times 10 to the 8 meters per second divided by v, which is 1.96 times 10 to the 8 meters per second. And this is a job for your calculator now. And after dividing the two numbers, you should get approximately 1.53. All right, and for our paraphrase, we'll write a therefore statement. So the index of refraction of sodium chloride is 1.53. Okay, so just as a summary over here, we learned about two ways that light can interact with the surface, refraction and reflection. We should sketch the normal as well, which is that dotted line that's at a 90-degree angle to the surface. So in the case of refraction, light passes through the material. As it does so, it can bend. Whereas in the case of reflection, light did not pass through the material. And if we're dealing with a plane mirror, light reflects off of the surface at the same angle it came in at. All right, that's going to wrap up this lesson. Please try the following for practice. Once again, any questions, don't hesitate to let us know. Thanks everyone, and we'll see you in the next video.